Did you know that almost half of our body mass is made up of muscle? As I'm speaking to you right now, I'm using muscles. And as you're sitting on your chair, listening to me, you're also using muscles. Our everyday life depends on our muscle system. I'm Valeria, I'm a molecular biologist, and I'm studying the process of muscle formation, which is called myogenesis. Myogenesis starts before we're born, when muscles are created, and continues until we're old, to keep them healthy and functional. Unfortunately, serious injuries, muscle diseases, or just aging can disrupt this natural repairability. And as of today, there's not much we can do to gain it back. So, understanding how myogenesis works, it's key to find ways to help a muscle recover and stay strong. Okay, but what is a muscle? Well, a muscle is an assembly of many muscle fibers, each one made up by thousands of tiny cells fused together. To be able to fuse, each cell needs first of all to become longer and bigger, and then to move around looking for the ideal partners. In these very important steps of changing shape and moving around, cells rely on their own internal skeleton. Even if we, as scientists, know a lot about the factors involved in this complicated process, there are still many blind spots that stop us from having a full understanding of it. And here is where I come in with my research. The blind spot my research aims to clarify has to do with a protein called EB2. EB2 is a quite mysterious protein. We know that somehow it helps shaping cells' internal skeleton, and we don't know exactly how. But also, we know that during myogenesis, cells get rid of it, which might sound a bit strange. After all, why would a cell discard a protein that helps manage its internal structure? I'm looking for an answer to this question using cell culture, a technique that allows me to grow different types of cells outside of the body in controlled conditions. In my experiments, I remove artificial EB2 from my cells and I check what happens. What I can see, funny enough, is that without EB2, all cells, even non-muscle ones, seem to go through the same changes of muscle cells in myogenesis. They undergo a transformation that makes them larger, more elongated, and more organized in space. This could be an indication that the removal of EB2 is a crucial regulatory step in preparing cells for myogenesis. If that's the case, by understanding this mechanism, we could potentially discover new ways to help muscle repair and regeneration.